everyone, and thank you for being here with so great numbers. This presentation is about the art of zip fuzzing and vulnerabilities found in VoIP. It appears that my partner Ejovi Nuyer had so great parties last night that he's still coming, but we don't want to keep you waiting, so let's go forward. He will certainly introduce himself once he gets here. What this presentation is all about is about the real vulnerabilities found through fuzzing in real life SIP auditing engagements, and that's something that Ejovi is about to talk more about. What I am about to present you more with okay. Just hold on a second. Slight technical problems, but where do I have it? I think it's fixed. Let's try the other one since this is too loud, I think. Right, now this seems better. So, what I'm going to say a few words about is what kind of inputs you should feed not only to SIP protocol, but basically every other protocol. And in this case, we are concentrating on the ASCII-based protocols. Few words about myself. I have my background in Oulu University, Finland, in a Protos research project where I worked until 2001. After which I have been working with Codenomicon Limited, that is a spin-off company from Protos research project producing robustness fuzzing, that is testing tools for basically whatever protocol interface. So to start with, I think it would be meaningless to talk about these things without actually having some real-life actual examples that the things that I am going to show here are actually working. So let's start with that one. After that, I will shortly cover, that would have been the Ejovi's part, the current state of the VoIP security, and then actually go to actually the funny part, that is the fuzzing of the SIP. So the test setup that we are having here is two user agents, both being open source. We didn't care to go after the commercial ones, CCs that we are. Then we have one infrastructure component, SIP proxy, and with these, I'm going to demonstrate the loss of availability. We didn't really go into actually investigating the real security implications of the flaws that we found. So basically, what we are demonstrating is denial of service, and about all the flaws that we are showing here, the vendors has been notified. We are actually releasing, once Ejovi gets here, the actual PDUs and some other example PDUs that you can use as an example of how to do different kinds of anomalies or fuzzing things to the SIP PDUs. So here's the test setup, and since I only have one laptop, I have a VMware running here so that I'm actually able to show what takes place. So let's have a look. So let's first start the user agent. So first we have this Povida.org's SIP user agent, which I am sending a SIP message, and okay, it does say please restart. Doesn't look too bad, and it probably isn't, at least from the security point of view. It's probably just some assertion. But if you think of the how VoIP is going to, or SIP is going to be deployed in near future. Just think of the mobile phone and how VoIP is coming there, and having that kind of things to your mobile phone is, well, it's at least bad for your brand, I would imagine. And at least annoying to user and pretty hard to call as a seamless service experience. Okay, then we have the infrastructure component. That is the party SIP proxy, and when it's being delivered, again, the SIP message, that is probably something it shouldn't say. So there again, we demonstrated the denial of service for the SIP infrastructure component, meaning probably that all the subscribers in your SIP or voice over IP network would be unable to connect to each other. Finally, let's have the second user agent. And when it receives SIP PDU, again it crashes. This time it appears that it's not direct buffer overflow, or at least we are not overwriting return address, but at least we could write some bytes into address we have specified. And the purpose of these few practical presentations that I showed here was really not to show that, these programs are buggy, since it is my firm belief that there are flaws in software, there continues to be bugs in software. What is important to come up with methods and tools that we can actually use to fix these flaws beforehand. And that is in essence what I'm going to present here. Methods that you can use to build your own fuzzing tools, own fuzzing testing materials, to make sure that the software that you are going to release or your equipment or software that you are deploying is safe and secure. Let's close. So this was something that I hoped HOV would have had few words about, but I tried to be his replacement here. So current state of the SIP, I think SIP is really going mainstream, and real big vendors, in my opinion, are doing fairly well in making sure that their software and equipment is up to the task. I talked about this into great lengths with HOV last night, but there is with some telecommunications operators and vendors, there appears to be this lack of I would call it that they have this burden of having those closed SS7 and old sign-on networks, which were pretty much closed, at least in theory, and therefore there is I would call it lack of understanding to realize how open this voice over IP infrastructure really is, even though that it might be run internally in the core or backbone networks. But when it comes to products, the smaller companies compared to large ones, they, I think, have less resources to do and have security teams to take care of the products that they are making. So there might be difference, but with black box products, it's often pretty hard to tell. And that is one of the key factors that you can do with fuzzing tools. You can actually take 2 products, 3 products, 4 products, put them next to each other, similar to what we saw here and actually compare how they manage when they are being run against with a test material. And of course it's not probably the only decision when you want to buy the product or deploying it to decide which one is better, but with that you at least get some idea of how good the product is. And most importantly, you can really compare how good the vendor is in reacting to the security problems. I won't be talking about this military and private use since I don't have no idea about the military deployment of SIP. Progress since 2001. I think SIP has gone ahead a great deal. Protos did find most of the basic flaws, but since we saw that we are still locating lots of new problems, they exist, and we have been able to improve methodology a great deal. So that what comes pretty soon here is the few things that you can do to improve your fuzzing sets so that you can raise the baseline of making the security and reliability of your software much greater. I won't go into this back to 99 portion too much. So let's go to our testing approach. What we saw here is that here you see actually the products that we evaluated with the tests that we created using the methods that I'll present soon enough. ZipExpon, PartyZip, ZipProxy, ZipSet, Linphone, and a couple of commercial products. For all of those, the vendors have been notified, and they are producing the fixes, which unfortunately are not yet available. So that's why I wasn't showing the exact PDUs that were sent to the implementation. Few words that I want to say about fuzzing terminology. In my opinion, all fuzzing is just a form of negative testing. It's just a slight automation of trying to meet this really hard to verify requirement that software must not crash, it must not do anything unexpected when it's being operated. I see negative testing when done normally as something that you do manually. You try this -1, you try very long username, you try invalid username. Fuzzing is then something that you do random mutations to the input data that gets to the software. Then there are advanced forms of fuzzing. iDefense guys, which hold a great presentation about image format fuzzing, called it advanced fuzzing. We call it also robustness testing, but regardless of the name, I think in essence the next step with fuzzing is to have this structure of the tested messages, files, whatever, modeled in enough detail that you can actually do reasonable decisions based on data types and everything of what to insert. Let's not go into that one. Few words before going really into the fuzzing of the SIP. It's when doing negative type of testing, it's usually not only enough to think of the actual messages that go to the implementation. It's an environment that affects a great deal the test results. Well, there is obvious example. If the service you are testing it is not turned on, then it's probably not going to handle the messages. Even though that we have seen services that you don't even need to enable, that they actually pass the message, so that you can just actually send your message, and even though services are not enabled, they still receive and appear to pass the message and crash. Other things, well, given that you have the services on, when doing this fuzzing tests, you probably should enable all possible features and all possible things that you can enable for your implementation, so to make sure that the test cases we send test the implementation as well as possible. Since, one example that is quite relevant with fuzzing SIP is this transport thing of zip. Zip was originally defined only for UDP transport, and in later zip specifications the TCP was added, and that brings few quite interesting scenarios with it. With UDP you are limited to 65 kilograms to the maximum UDP datagram size. In practice that's even less for most operating systems, which by default limit UDP packets that are received to 4 or 16 kilobytes, and you actually have to modify them to be able to receive larger ones. But with TCP you can actually practically send as long username as you want, as long any other value you want. So just imagine zip proxy that has to convert traffic coming from TCP to the UDP. So just send the username of 100 kilos inside zip message to the proxy and try seeing how it handles converting that into the UDP, into the user that is registered over the UDP. So there I want to point out that environment is something that you should never ever forget when doing testing and while doing fuzzing testing materials, and more importantly when running them. Okay, I'll talk about that. So I think now we are getting to the interesting part. What I am going to present is, well, what's all the fuss about? Still few words about what parts of the software we are testing with fuzzing, what kinds of flaws we are finding, and so on. Then few words in deciding what you should fuzz, what kind of things you should consider when doing decisions on fuzzing something. Then there is this isolated bug fault model thing that I want to say a few words about. Importance of systematic approach. As said, I'm really a believer of doing these things systematically compared to random mutations to the input data. Then ZIP is an ASCII-based protocol. It brings something with it which you can take advantage of when designing your own tests. And then finally, different types of anomalies which you really should put into the PDUs. At this point, I would be interested to know that how many of you guys here have been running any of the fuzzing tools against the ZIP implementations? Okay, there is at least one. Has it been Protos or something else? Okay. So let's see. Well, how many of you are using voice over IP in any capacity? Okay, there is slightly more. So what's all the fuss about? I think the fuzzing is, in essence, the last line of defense to make sure that the software that you are using or deploying is safe and secure. It is such that you can actually rely on it. You can use fuzzing you can use it as part of product development, which is, in my opinion, where it should be used. You can even still use it when you are deploying voice over IP-based systems to make sure that the hardware and software that you are getting is safe. And when you look at the picture there, you get the idea of what kind of elements we cover with fuzzing. The black background, it shows the infinite amount of tests that you can actually create to test different kinds of things for basically any network protocol. Just think of the 4-byte protocol, imaginary 4-byte protocol. You have minimum of 4 million tests with that one that you could send with 4 bytes. Let's imagine that we have like 2 different states. Then it would already be 8 billion potential tests. So that said, I think with any reasonably complex current protocol, the amount of test cases that you can generate is infinite. And that tiny little dot there is the positive tests, meaning like depth in the source code, which you need to prove that you meet all the requirements. When you enter wrong username, you don't get in. When you insert the correct username, you are authorized to log in. To get the code coverage metrics, to see that all the branches are executed, and so on. But with fuzzing, what you get is you get the breadth of the source code tested. You don't only get test that you take all the branches. You test all the functions with the different kinds of values as to get not only the coverage good, but also the input space of the program tested well. And there, in my opinion, is some misunderstandings about the purpose of the buzzing. Some people think that it's all about making sure that there are no security problems, but I do see much far-reaching purposes for that. That is to locate as early as possible from programs, crashes, performance degradation, and any other possible problems that you can come around with doing that kind of negative tests. Since, okay, we are security people here, and it's, of course, if we find security problems, it's essential to get that fixed. But since with the very same tests, you can easily locate null pointers, any other problems that result as a crash, which are nevertheless annoying and in some circumstances very likely security problems. So let's use these methods that we are presenting to actually not only fix security problems, but to make software better as a whole. So that said, what to buzz when you are thinking of the voice over IP? It's not only the SIP that you should think about, but rather your voice over IP deployment. What interfaces you actually have there? What are the most critical ones? What are the most open ones? And there it comes down to the risk assessment. It would of course be preferable that you would have ready-made test materials for practically any interface that you are having, but since that's even nowadays not a reality, there has to be decisions made into what you want to test, and there a good risk assessment using any available methods is probably something you want to do, and then go after those interfaces to make sure that they are reliable. When you have identified the protocols that you really want to test, then there are few hints that I want to give. Only do your tests for the actual behavior. When you read the SIP specification, there are like at least 45 different headers that are specified for SIP. Just check your source code, what you are actually using. So test the features that you are implementing or is being implemented. Of course, when you are not having, well, since that's where the complexity is, it always pays to do few tests for the headers and features that are not being implemented, just to make sure that the programmer or implementer hasn't really tried to put something there, coded some small stuff to handle that unused feature, and then forgotten it altogether, where there is then some switch case or something without default branch or anything, and you end up then again crashing. So that's something that I want to stress. Stress the functionality that is really implemented. And what is really implemented? There are a few ways to really find that out. Best would of course have source code available and maybe use some source code coverage tools. GCAP, for example, works quite well so that you can throw your material against the software and you can actually get to see which parts get covered, which doesn't get at all. One additional good thing about that is actually that you get to see the really important parts of the code, those that are actually being able to be tested using external inputs. Then when you are doing things for the protocol, it's always good to check your common sources of information, CVE, bug track, see what has worked in the past, since people end up doing same mistakes again and again. Okay, yeah, there's a few tips for SIP. It appears that ever since 2001 or so that we have been doing fuzzing testing materials for SIP, it's always, these are like the top headers that you end up finding problems with. And again, there's no, it would be quite easy to guess why they are these. These are the ones that probably has most complexity, require most handling by the software. Most code is written to handle parameters in these headers. And as said, the bugs are where the complexity is. Now, isolated bug fault model. It is my belief that you can't test everything at the same time, nor can you do everything in the same message element. What I mean with this is that most of the bugs, I don't say all, since that wouldn't be true, but most of the bugs in the software can be triggered with only one exceptional element in the message. That doesn't say that you shouldn't have the rest of the parameters correct, but most of the bugs in software can be triggered using this single fault in the message. There are, of course, situations that you will want to have multiple exceptional values embedded in the message, but most of the time I would prefer only having one. The reason for not having multiple ones, like in 2, 3, 4, 5 location, is that if you look at the picture, there is this decode input syntax checking. Just imagine zip message arriving to the implementation. We have anomalies like very long overflow in to and from headers. If there would be only long to header, we might find a problem in the handling of to header. But since we also have this very long string in the from header, the syntax checking already decides that, okay, there is a big bug in the message that we are receiving. We are definitely not going to handle that one, and just throws it to the floor. Maybe response, probably not at all. And the anomaly that we have inserted to the to header never gets to trigger. So what I'm saying is that normally it pays to try a really bad exceptional element anomaly in only a single location in the PDU. And only when you are certain that you understand how different things affect each other, then really go after having them anomalies in multiple locations. There are other problems also with having multiple anomalies in the single message, since it really blows the amount of test cases you are about to generate with your fuzzing tools. Then few words about necessity of the systematic approach. What we are seeing here, the top line, that's what you saw on Backtrack like 96 when people were finding problems from HTTP servers. That's something we are still seeing on Backtrack. So there has been, in my opinion, very little progress in how people really attack the different elements of the software. Whereas compared to the lower ones, there is a to zip header from zip headers, which has been exploded into the different parts to highlight sort of, you could even though that it's ASCII, you could even consider them as a data types. There is like zip, which is the scheme portion of the zip URI. You can have your separate anomalies for it. There is separate enumerations in the specification that you can use for that one. Then there is an user portion, which is an ASCII string, which is again handled by different parts of software, probably raising all the way to the user interface, so that code in user interface has to actually do something with it. Then there is an optional password component, which again has to be passed by different parts of software. Then there is the host component of the zip URI, as well as HTTP for that matter, which can be either symbolic host name for IPv4 or 6. It can be real IP address. I suppose it could be something else as well. It contains the @ character, which you can, well, it's an @ character, but nothing actually prevents you from putting huge amount of @ characters over there. And the host component is then followed by the host port component, which is optional, but then you can actually have illegal integer values also inserted to the zip URI. And all those, the zip message parser has to handle reliably. So there's a simple checklist to actually apply these anomalies to the PDU. So when you have the element that you are going to anomalize, make tests for, identify the substructures there, required, optional. Then based on that, identify the data types. Okay, this is ASCII integer, this is integer, this is ASCII but it's used for something else in the user interface, so on. And then based on that, apply the anomalies that you have for that kind of data types. In addition of these, there are lots of structural and structural mutations that you can do. We cover those later on. What ASCII, as in SIP, brings to the table, in my opinion, it allows various levels of freedom compared to the binary protocol. I don't particularly like ASCII-based protocols. I would always choose a binary-based protocol, but I'm open to discussion about this after the presentation. But few problems with ASCII is, in my opinion, that even though that it's human readable, we tend to write specifications so that it's not impossible to be machine parsable, of course not, but at least quite difficult, which forces us to do like really good parsers to get the message elements really parsed into proper containers and so on. I think when you think of the original idea of HTTP was like really nice, have this type and value, but just think of the via header, to header of SIP. There's a type, to, and then there is a huge amount of structure, different components, header parameters, everything inside this value part. And that really adds complexity to the parser. I don't know if people are actually using lectures or something to parse the SIP message, but at least some implementations that I have looked use handmade parsers, which in my opinion is always a bad choice compared to using real syntax or lecture to get the elements in the message part. One other thing regarding ASCII, since, well, again, think of the binary type length value encoded message. You may have 8-bit, 16-bit, even 32-bit type field. Okay, you maximum get 4 billion different test cases to try all the possible values in that field. But then thinking of the HTTP SIP, again, you can have like practically any so long header name as you possibly want with basically any character. So there you can do infinite amount of test cases, which probably wouldn't make any sense. And that really is something that you want to. That is something you really want to think when you are doing the presentation, meaning that where to put the effort. Do I want to like try white spaces in all possible locations that they are allowed, since they are allowed practically in any location, or actually go after the real structures and real elements in the message. Regarding SIP, there is this session description protocol that is embedded into the SIP. There could be MIME multipath bodies for tunneling, ISUP content for telecommunications networks, and so on. So when doing parsing for SIP, do consider them separately. I have no strong evidence about this, but if you know the Protos results, there were quite a few errors found from the session description protocol tests, and it is my guess that, well, it could be that the people that wrote STP parsers are just much better in writing code, or it might be that it's slightly simple to parse. It might be both, but I think why it wasn't that effective is the fact that the phone calls weren't really established. So the values in the session description, the code that handles session description wasn't really used. So when doing anomalies, for example, the session description, always make sure that you actually, when there is an anomalized or exceptional session description in SIP message, you actually initiate the phone call so that the values there really get used. Now, this is like a really interesting part. What kind of anomalies to really input into the messages that you are creating by parsing? For each of these basic types, I'm going to give you a few of the examples extracted from the context and then insert it also to the SIP message. what I'm covering here is standard overflows, meaning like basic ASCII-based overflows, C-style format strings, other control and non-ASCII characters, and few broken UTF-8 encodings. Standard integer anomalies, basically most importantly something that you can do with ASCII-based protocols, then few address examples of address anomalies, then those structural things that I was mentioning, and then few words about how to come up with really protocol-specific anomalies for SIP. And with these, you will notice, when I'm going through those exceptional elements and anomalies, you will notice that there are variations of those elements. There are like 4-character version, 16-character version, 128-character version, and so on. And why do we want to do that? It's essential to do that since there are different lengths of strings in messages get handled by different routines. So that whereas one routine may reject 128 character username, the other routine may decide that okay, now that it's 4 kilos, it's so long that there is certainly a really bad error in the message that we received in, and decides to construct a return PDU where the return PDU construction routine then it fails. So that's like one of the most important things to get the messages tested with different lengths of strings. Not to mention that when you are testing different applications, you are like, hi, read the shift. Yeah. Well, let's keep going. Yeah. So, we are now getting to the standard overflows. What we have here is like ASCII-based overflow. We can have alpha or alphanumeric overflows there. There we have below C-style format strings with both buffer expansion and the pointer arithmetic ones. Few things I want to point out there is, for example, this ASCII-based overflow. People usually end up using this A or 61 in hex. I don't know if it's due to the fact that Alex One was using that long time when he wrote this, exploiting the buffer overflows for fun and profit. But one thing I'm telling you is that you should probably also try characters other than A, since, well, you are not going to believe this one. This is I saw this in real life. So I was in CPIT like 2002 or something like that. There was this one vendor that noticed, okay, our implementation is doing buffer overflow here when they received this 1024 characters of A, and instead of really like thinking that what's the flaw, how to fix it, they just wrote a check in that, okay, if we receive in this element this 1024 A's, then we don't do anything. And but if that had been changed to B, they would have been like in problem again. So try also other than A as well. Okay, then there are those control character things. I don't think that you usually end up finding with like buffer overflows or stuff like that with them, but you do really end up finding pretty bad flaws there. Meaning like this hex 7 is one of my favorites. Does anyone know what character that is actually? It's a bell character. It really makes fun when somebody logs something to the console without actually filtering that one, and it really takes your Windows and Sun mainframe down when it logs to the console, and having like a receiving like 4 kilos of bell character, not to mention that the administrator is pretty crazy when the machine starts going beep, 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 beep in the machine room. So, and there on the bottom we are seeing the one example of the ASCII overflow applied to SIP message. Well, you can take any of the present SIP ones, for example, here, and then use your integration to actually modify them so that they fit there better. Okay, then for the integer anomalies, Okay, there are the standard ones. Something you must not forget is the ASCII ones. Even though that you can basically put in as big and as small ones, you can with ASCII you can always put in negative values regardless of what's the actual enumeration or meaning of the field. And the other important thing is that even though that it's ASCII, since it's computer program, it still has internal binary presentation for the value. So still think all the values of boundary value testing. Try maximum, minimum 16-bit, 8-bit, 32-bit, even 64-bit values, as to get sure that you don't get any signed, unsigned problems with them. Then you can, since it's ASCII, and since you can throw in floats, which are most of the time probably quite confusing to the program, and also introduce some unexpected numeric systems, like just throw in hexadecimal binary, or then the which is the last zero value beginning with zero, that is octal value to the program. In practice, I haven't seen that many problems with those ones, but there has been anyway. Addresses, okay, IA, NA, here is our friend. From them you get nice lists of reserved addresses and address spaces. In addition to that, you can, you have lots of chances to use those integer and overflow anomalies with how the addresses are being constructed. And the example that we are seeing on the top right is the the IPv6 address that caused that was pretty something that caused, for example, Apache 2.50 or something crash. There was some time back ago problem with Apache web server with handling IPv6 addresses, which was actually in the IPv6 handling library, and that is the exact test case that causes that flaw to trigger. Then the structural anomalies. Always go for repetition in headers and their sub-elements. On the top you see the CSEC header, which is then being repeated huge amount. Well, its value has been repeated huge amounts of times, and it's sometimes quite confusing to the general purpose parsers, where you are basically just passing in headers where you expect not to receive more than the values that are marked in the black there. Then of course there is a repetition of header, which you can see in the bottom picture, and those are specifically for the, I think, embedded devices or devices with less processing power, quite effective, since even though that you may not be finding the actual flow in the code, it sometimes to process that kind of repetition takes so long that the watchdog processes in the small embedded devices think that, okay, the process handling the repetition is taking so long time that it must have gone into infinite loop, and it actually reboots the device, or at least the process. So that is a good example actually from the fact that with fuzzing you do end up finding flaws that are not directly attributed to the code you would be reviewing in the first place. Just think of the crash that is just triggered due to the unexpected CPU consumption, which if it would be allowed to continue, would go out just okay. But since the watchdog process thinks that the software being tested has gone into infinite loop, it will actually reset the inside the device.
I think in voice communications, especially, something like SIP, they're probably going to find a lot of bugs like this because most of the developers aren't really coding too many checks into it because they're looking for speed. So you get a lot of problems where someone is writing code and they're saying, well, you know, as long as it works, and a lot of it is quality of service, right? It's like we only have so much processing power, we can't really build too many checks into our code. So you'll find problems like recursive errors that you see displayed here in a lot of SIP implementations.
Yes, that's very correct. And the last one, the middle example, it's just a root of underflow inserted to the signatures. So it's just been cut short, and I think most programmers, at least in context of UDP, you really expect when you receive the data grant that you have all the data that you should have there. So at least historically, that kind of things were something that really caused havoc. And now that I mentioned it, since I really forgot to mention this earlier, is that the classical buffer overflows that we are seeing with these kinds of standard ASCII anomalies, these we are seeing much less nowadays. I don't know if it's due to improved coding practices, improved education, better languages such as Java, which are slightly safer against this kind of problems. But nevertheless, we are seeing much less problems with the direct buffer overflows or problems with handling long strings. Rather, what we are seeing are problems with integer handling and more importantly with the structural anomalies.
I think that's I think that's pretty important because basically if you're going to be auditing SIP, if you're going to be auditing any voice over IP communication, you can't really find the low-hanging fruit anymore because most developers understand basic buffer overflows. They know how to spot it in their code. So what's really important about fuzzing, and I'm sure Mikko probably mentioned it already, is that you're going to find a lot of vulnerabilities that you can't see by looking at the code because you're looking at how multiple components interact with each other. So that's why fuzzing is really important when you're dealing with a really complex protocol like SIP. I mean, SIP is pretty complex. It's really hard to code because there's so much parsing involved. And if you're just looking at the code, and did you upload the test cases?
Yeah. Unfortunately, they haven't been able to get them, but...
Okay. If you look at some of the test cases, in order to exploit the vulnerability, you really need to modify two components of the packet, right? So that means that if you're just sitting there pounding away on A's or B's, trying to get something to overflow while you're watching it, it's just not going to happen. Because I think most, in general, not only, SIP developers and the voice over IP developers, in my experience in dealing with them, aren't all that bright. I'm sorry if you're out there in the audience, but it's just, in generally, most people understand basic vulnerabilities. But when it comes to really like integer vulnerabilities are really hard to spot by eye.
Yeah.
Sorry.
And something that we might discuss even during the presentation is how difficult it is sometimes to track the original cause of those problems.
Yeah, I mean, for example, one of the vulnerabilities we found, it obviously crashed the application, right? And at the first look, it looked like it was a buffer overflow. And it wasn't I looked at the code and I was like, wait a minute, it doesn't look like a buffer overflow. I don't see I don't see a fixed buffer size here or anything like that. It turned out to be an unsigned integer problem. That was totally, it was totally from another part of the SIP packet that was causing this problem. And problems like that is really tough if you're auditing an embedded device because if you don't have debug access to it, it can be a real bitch, right? Because how are you going to find it? With the vulnerability that looked like a buffer overflow, I had to run it through, we had to run it through a debugger in order to really find out where it was located. But, that takes a lot of time, and most developers won't want to do anything like that.
That's true. So, if we continue with these protocol-specific ones, how do you end up deciding what kind of specific anomalies for each protocol that I'm passing I should apply? Well, I have a simple answer. Go through the specification, go through it in detail. Just see what the other protocols the protocol is implementing, what specifications it's actually referring. Here you can see just a short list about things that I would definitely try with SIP. SIP specification very clearly states a number of token characters which are used for different purposes in the SIP headers, parameter separators, dots, colons, for separating port components, other components. those you can find from the specification, and to add confusion, you can pretty easily add them to quite different locations in the zip messages. Then there are those actually HTTP line continuations which are adopted by the zip specification and only actually specified for zip there. And with those you can do again really weird things. And I don't have first-hand experience with these about zip, but there definitely was vulnerability related to those in Apache web server. And given how much people really try to find problems from Apache, I wouldn't be too surprised to see similar problems with many zip implementations. If you look deeper into the zip specification, you notice that you can have these URI escapes in the multiple parts of zip messages, which, among other things, allow you to hide the element, hide the stuff that you are putting into the message. If there are, like in firewalls or somewhere, there are components to check what is in the zip message. It's classical stuff from HTTP to do URI escaping to actually hide those things. Beyond that, you can actually toy around with those URI escapings, do anomalies for those, and so on. Then there are these embedded base64 encodings in authorization headers of zip. Again, you can hide values inside base64 encodings, but more importantly, you can also anomalize the base64 encoding itself.
I would look for these type of bugs, I think, in like in soft phones or hard phones. Like if you get a service like Packet8, they probably make the actual device really lightweight, so it's not full protocol spec. Just because they're assuming that that device is always going to be talking to their proxy, right? So they're just saying, well, our proxy is never going to send anything other than this. But, you know, if you're us, right, you're going to send a lot more than that. So you might find a lot of vulnerabilities if you're looking at devices like that.
That's true. Then we have the UTF-8, which is pretty ambitious nowadays. There is actually, you can do a number of things. You can just throw in very long euro sign or any other UTF-8 encoded strings. In addition to that, you can, just as any other encoding, you can break UTF-8. And there is actually a URI, which I suppose you can see if it's so small, but there is this quite excellent UTF-8 test page in the internet by this German guy, at least originally, which I really recommend you to go through when you are designing any tests for the UTF-8. Then there are other zip-specific escapings. There are none that these doesn't come from specifications, but it appears that many implementation does understand when you have \0 something. So it's something that you want to make sure if your implementation supports it and generate test cases for it. I already mentioned those session description parts. That's actually something that is being embedded into the zip. So that is also something you definitely want to test. But beyond that, the zip can actually, just as HTTP and then many other similar protocols, have different content encodings based on what you specify in the headers. Basically, I think you name it. Just go through the specification and actually look your implementation. What it handles, what kind of messages it sends, what it receives, and then do your fuzzing decisions based on that. Okay, here we have a few examples. I think all of these have in some context caused trouble with the zip implementations. On the top left, you see the invite message where the scene component of the zip URI has been changed into the HTTP. That is definitely something that is unexpected, but not definitely so unexpected that you should actually crash with when receiving that one. Then there is a zip token character anomaly on the rightmost picture. There is a tiny semicolon inserted in between invite and the zip URI, which probably signifies that the zip parser really thinks that the first header parameter or zip URI parameter is really starting after the invite method. And what we ended up with that one was that there was a null pointer exception due to the fact that the since the implementation started to pass immediately, the zip header URI parameter, it never actually read in the zip URI, which was due to some missing check left totally uninitialized. Then there in the bottom you can see the URI escaping and then the base 64 encoding both applied to the authorization and from headers. Inside the base 64 encoding there would be a C-style format string and I don't recollect what's inside the URI escaping, but it's something. But well, there I hope I briefly was able to show you some of the very basic things that you should, when you are doing fuzzing testing materials for practically any protocol, ASCII-based protocol, things that you really should try. So the guidelines I would want to give you is see the substructure and then think of the data type and then have very good presentative anomalies to cover those elements and those data types that you have identified with the modeling of the elements. And that's it. It's not everything. I would really love to quote Boris Beitzer, which is one of the great guys, I think, with this. So, tester, break the software as you must and drive it to the ultimate, but don't enter the programmer's pain, since, in my opinion, it's a lot more fun to actually break the software and cause pain to it rather than actually implementing it. So that's something I really want to do. But if we want to go to conclusions here about this presentation, not only regarding the how to write the anomalies, so VoIP is really going prime time, don't you think?
Yeah, I mean, the basic issue is that parsing VoIP communication is just really complex. It's not easy to do. And if you take it into, it's not easy to do securely, to be correct. It's probably easy to do if you know how to, write parsers, but it's not easy to do securely. And a lot of the vulnerabilities that you're going to see now in voice protocols and applications are really the type of things that you probably saw in like 2001. I know Miko did a really big project in 2001 and found a number of vulnerabilities in a lot of the VoIP software that was out there. But we did our testing like 3 weeks ago, and we found 8 bugs in some of the major stacks that's currently being used by most vendors out there. In one commercial vendor that I contacted, I don't know if Miko told you this.
Well, I very briefly mentioned, but you can, please elaborate.
Yeah, I send them an email. I say we have this 30-day policy of noticing vendors, giving vendors time to patch their systems. And the guy says, talk to our lawyer. That's like something you would get in 1999, right? These are these guys aren't really used to. Some of these vendors aren't even used to having, their hardware exposed to IP networks, let alone having to deal with attackers that can exploit their systems. A lot of vendors in the telco side are just buying IP stacks or voice of IP stacks from third-party vendors. They don't really understand what's happening on that stack, but they know to just plug it into their system and okay, now they're voice of IP compliant. They can sell to the military. They can sell to their big corporations now, and they have no concept of the security involved and the flaws that are on those systems. So a lot of the vulnerabilities are, buffer overflows aside, are going to be vulnerabilities that you probably saw 3 years ago. But the bigger vendors get it. Companies like Cisco. I've never worked with Cisco, but companies like Cisco or even Microsoft probably get it because they already have the threat model in process, right? They already know how to audit code. They already know how to deal with vulnerabilities. But I think the vast majority of the voice of IP vendors are not big companies. They're 20 people, 100 people companies, and they're using these third-party stacks because they got to get that product out there. And it's all about service. It's not so much about having a unique stack or anything like that. It's about having the add-on service. So they don't really care too much about securing their code.
Not to mention the fact that lots of open source stacks probably has been utilized to build different zip products, which this is the conclusions I think, but nevertheless they have been forked in the past, and it has been working quite well. And the guy that do the fork and did some modifications for our stack left company a year ago, so we don't want to touch that. And even though that we actually get the original open source or whatever stack fixed, it does not always, I don't say that it doesn't at all, but it doesn't always really propagate to the forked code base.
Right. So I mean, you're gonna have like you're probably gonna meet some vendors that are saying that we don't really use open source stacks because sure it's like a variant of it. We started with that like 2 years ago. And they're probably going to have the same vulnerabilities that were there 2 years ago because they don't follow the security. They don't follow like anything related to security on the stack that they originated from. So, like the test case, we gave you like Miko uploaded the test cases. Basically, I mean, we gave you how many did we?
There's like 25 examples.
So I mean, there's 25 example packages that you can basically download and run and go take home and run against your SIP products. And I'm pretty sure that you're gonna find at least one bug. As a matter of fact, I will pay you $1 if you don't find one bug. Just come to New York and find me. I will pay you $1. I swear.
Okay, so that said, I think if you are deploying voice over IP products, really ask your vendor, have they really developed their own stacks? How they are really testing them? Have they only done like conformance testing or taken additional measures to really make sure that it's reliable? And whether they have like forked their code somewhere or really developed it by themselves. But beyond that, I think you know this much better than I do, but voice over IP is not only the signaling like SIP or MTCP or H323. There are like lots of other things involved as well, which when deploying a voice over IP solution, you really should think of. There are like signaling, there are management, there are HTTP, SNMP, other protocols that are used for management. And then there is of course the underlying IP stacks and everything. And when you are thinking of the really secure voice over IP solution, I think all those should be in very good shape. Then of course we have this presentation has pretty much covered only the implementation problems in voice over IP requirement and how to actually tackle those, how to design test materials such that you are creating effective tests. But beyond that, there are of course, I think we call that the implementation flaws in the actual stacks are pretty fundamental. But beyond those, there are like number of flaws which.
I mean, we could come up here and say, voice over IP is insecure, someone can capture your data, but everyone already knows that, right? I think what's really critical are the coding flaws that are in nearly every voice of IP or SIP product. I think on the market right now. I mean, with some exceptions. If you're talking about like interception or quality of service, denial of service, I'm really afraid of the military deploying voice of IP. That's my major worry. I mean, like I know there's a directive from Donald Rumsfeld that says that the U.S. military has to be like a voice of IP and IPv6 for like 2012, and I don't know, like if someone's going to drop a bomb, I would want to make sure that you can hear them. But we're still in the fundamental level. We're still not at a point where you can reliably guarantee voice of IP communications, and that's a totally different issue from the coding flaws that you're going to find in most of these products. But that's just my only gripe about things outside of coding.
Yeah. But I think this is pretty much it, and thank you for being here so that you managed to come to the last minute, and I hope it was good parties last night. Sorry for being like